pictures of me and you.
I like how you're thinking you might prefer that.
This one.
Oh, there we go.
This hasn't got camera filter.
What was it? Yeah.
This is
BATK
XD, I think.
This is Google thing.
And you repeat CA, CK, XB.
Told you.
Right, so you guys were all at the last section. So, last session was like hello and stuff like that. This is the first lecture on the course, okay? So, as I might have said last time, it's me, it's Linda Smith. Colette, has anybody met Colette yet? She will be down in 0T134, whatever time you're scheduled to go down there. And she's very knowledgeable, of course. She's into deep learning in a big way. And she will help you a lot with LabVIEW. Now, this course, I'm not really going to assume you know much about it. I'm just going to start from the basics, really. So, of course, the lectures are up here in 4Z12. And the tutorials also started today, as I just said, downstairs this afternoon. And what I thought we'd do in the tutorials, what we normally do, is I start off with Vision Assistant. Okay, so you get into Vision Assistant. Now, Vision Assistant is like a vision system, right? It's written in LabVIEW, and so it's got all the functionality of LabVIEW, but it's easy to use, right? So it's like a gentle introduction to machine vision or vision systems. Okay, and you'll find it quite interesting to use, I think. It's got an online tutorial. Okay, so go through the tutorial today, start using that, and all the iMac vision tools. That's the vision system part of LabVIEW. Okay, so LabVIEW comes with all these tools like a threshold, and there's hundreds and hundreds of tools, and they're all available in a Vision Assistant. But the advantage of Vision Assistant, rather than writing code or G code, which I'll tell you about later, you just drag it down from menus. Okay, you drag it down from menus, and you can experiment in real time. I mean, when I started doing some vision in the Cranfield in the 1980s, it was like we had to do it in C. It was like a nightmare. You know, you write a bit of C. Run it, see what happens. If it doesn't work, you try and write a different bit of C. An absolute nightmare. Compared to this, where you just have your image in front of you all the time, you're running different functions and menus, and you're seeing what's happening as you go. So, right then. So, if you've got any questions, you can stop me as well, okay? Now, in addition to those two things, which are timetables, right, what I want you guys to do, which I mentioned last week, is to make use of the new UWE Machine Vision Lab, which is in this building. Now, you guys know, have anybody been to the Digital Gallery? You haven't been to the Digital Gallery? So if you go through here, right, on the ground floor, you go through those doors, you've got the rapid prototyping machines, right? And then you guys have seen those machines? Yeah, you go through there, right through, right? You go through another set of doors, and then you're standing at the top of the Digital Gallery, which you guys ought to go to. You've got to go, I recommend it, right? Because the guy in there, Andy Hill, he's really good. Actually, Andy Hill is really good. He's running the Digital Gallery. He lives, can you believe it, in a boat on the docks apparently. But there we go. And down in there, when you're standing at the top there, you look down, you see the UWE Machine Vision Lab, which I've rigged up with the help of Scorpion Vision. Okay, so this over in the corner against the wall, you can't miss it with the signs. I could talk a bit more about what you could do there. I'm not going to exactly tell you what to do there. It's just really capturing images and finding out about what cameras and lighting and lenses are all about. Okay? All sorts of different LEDs they gave us, which are very bright, so watch out for them. Watch out for the infrared ones. I'll talk more about that later. Okay? There are some infrared ones, which I recommend not using for the time being. Okay? So that's it. So you grab your images in the Digital Gallery, and then you can process them using LabVIEW, and that will be for your assignment on this course. I haven't put any details of the assignment in there really because we haven't actually written it yet, right? That's probably the main reason I haven't actually put details. But Colette and I have got a load of good stuff going on. We're going to go and see Josh on Thursday at GKN. Who's here from GKN? You know Josh? Well, he's going to, on Thursday morning, he's going to take us again to sort out this assignment basically. It's going to be industry-led. This will be a real problem that GKN are facing. It's cost them a lot of money. You guys are working on this assignment. So it's not something out of a book. It's something real world stuff. Any questions about that lot? So what I'll do then this week is I'll start from the beginning, as they say, and I won't assume a great deal of knowledge. What we're talking about is computer vision or machine vision, more industrial applications of it, you could argue. And I want to talk about different applications, various examples. 2D and 3D, right? Nearly everybody you'll ever find on this, and most of the books you'll ever look at, will be talking about 2D, just normal images. But in our lab, we got a niche for the last 20 odd years, which is 3D. So we capture 3D data directly and start analysing that, which we find gives you a lot of functionality over just using 2D. A minute ago, I just got out of a meeting a minute ago, I left early with a meeting from a company we're working with, who were looking at forensics. They look at all kinds of forensics. Writing, signature, forgery, serological materials, blood, and all the rest of it. And we got a PhD with them, 50-50, and it's very, very interesting, very good company. But it turns out, which I shouldn't go into any of this, because it's all meant to be secret, but 3D can offer, I won't go into the details, but 3D can offer a lot of information on how someone drew a signature or anything kind of writing. You know, which, if you got a cross in various points in their writing, which arc came first. We can get that information in 3D. You can't really get it in 2D. Nobody's doing that. So this new PhD guy, he's doing that. So as soon as he gets going on that, we'll have a paper straight away, a journal paper. That's completely new. No one's reliably doing that at the moment. So 3D gives you lots of functionality that people don't think about because it hasn't been much use of it in the past. And it gives you all sorts of advanced capabilities. One thing I would say is that the other thing we talk quite a lot about, and I'll talk about in the lectures, is deep learning. And the reason I talk about that is that there are two techniques that can give you advanced functionality, okay? Including some 3D data or using deep learning. You know, I've got this application in the field I keep talking about, grass fishing, which is going on in Scotland, where you're looking for the dock, you find the dock, and then you squirt a bit of weed killer at it. We thought, to start with, we were going to use some sort of fancy 3D vision system to identify that dock, you know, which is a different shape of leaves to the grass, of course, right? But we didn't use it, actually. We just used deep learning. Why do you think we didn't use it?
Doesn't need to use it?
Yeah.
The 2D image is good enough.
Yeah, exactly. That's exactly it. We didn't need to use it. I mean, you want to keep things as simple as you can. If you can get away using 2D images with some deep learning to do something you thought you had to get 3D, then you're better off with the 2D. Because when they start manufacturing this system that runs around on a tractor, okay, squirting weeds, if they just use webcams, it's going to be a damn sight cheaper, and they've got to start investing in these 3D cameras. So when it comes to commercial applications of machine vision, you probably want to keep the hardware fairly simple, or as simple as you can. Sometimes you need to go to advanced 3D and all the rest of it, but if you can do it 2D, then stick with that because it's going to be cheaper. I mean, every time you manufacture that system, you're saving money if you've got cheap, you know, you're selling at a certain value and you've got cheap hardware. Because the cost software, once you developed it, you don't have to keep developing it, do you? Well, you know. Once you got it working, you got it working. So that's kind of showing the 3D face there, and the false colour shows the orientation of the surface normals. Right? That's Gary off our website, I think, actually, that one. Yeah, so I go into deep learning quite a bit. Right, and this is exactly what I was talking about a minute ago, wasn't it? So this is it. And I'll be presenting the paper at a conference, and that's me with the paper. Not getting a big crowd of people, as you can see, unfortunately, but it was like a photonics conference in San Diego, and we were kind of a bit more, it was more about advanced lenses and stuff like that at the conference. That's my excuse for not getting a big crowd. Right? Yeah, so that's the grass vision application, which is now being commercialised by this farmer in Scotland and a company he's running. And you're going to be seeing it everywhere. He's not the only person trying to do it. You know, it's going to be, in the future, they're not going to be spraying herbicide everywhere. Do you remember last week why we said they don't want to go spraying herbicide everywhere?
It's bad for the environment.
Yep.
And it costs money.
Costs money, yep. Farmers are particularly worried about the matter. Yep, that's exactly right. What else?
Stops good things growing as well.
Exactly, yeah. Clover, it kills all broadleaves. The clover is good for the soil and good for the animals, actually. So you don't want to kill that. So there's a lot of incentives to doing this, really. At the moment it's weed killer, but you could, as I say, use other techniques, microwaves, or just hoe it out or robotically, perhaps. You know. Well, that's the paper I keep shouting about, trying to get some praise off people. You know. But it's quite good at going and doing research, because although research is difficult and expensive and takes a hell of a time, you do get interesting things going to conferences, and it is interesting to publish papers and books or whatever you're into, you know. So this is the kind of stuff we've been doing. And this is the kind of thing I put these up on here actually last night. This is a website that Andy rigged up, my son Andy rigged up, which I thought was quite good using bricks. This is the official part of the Bristol Robotics Lab website for us. So that was rigged up by them. And this is also information about the UK IVA. So they have these every once in a while at the exhibition centre in Birmingham. They have these big exhibits of industrial machine vision, which is quite interesting if you're into this. You can go and see the latest hardware and such. And I think that's a list of groups around the country, around the world, doing research and machine vision groups. In the library, there's some stuff you might find under these books: engineering section, computing, and then journals. IEEE is normally highly rated, of course, as a journal. Image and vision computing, we're publishing in these journals. So that's just further reading. So when it comes to this module, I don't want you to memorise what I'm telling you in the slides. What's the point? I want you to read around as well. Read around in books in the library, on the internet, and try and get other perspectives on what I'm talking about. There's a lot of useful information on Blackboard. I'll put a lot of links to papers on there and such. Oh, these books are in the library. I managed to get them to buy these. Some of them are a bit out of date, I'm afraid, but a lot of these techniques don't change too much sometimes. Image processing handbook's good. Image processing with LabVIEW, that's what you're doing, of course. This is quite good because it's got a lot of, when it comes to machine vision, if you go to a conference, like I said last week, everybody's doing deep learning. They're all doing CNNs. But I wouldn't overlook traditional machine vision. Right? And that's why I get you guys to use Vision Assistant and go through all the traditional machine vision, computer vision techniques. Because, again, right? Well, again, why would I say that? I mean, why am I saying that you don't always have to use deep learning?
Because they work.
What works?
The older version.
Yeah, exactly. So what does that mean if they work?
That they're kind of simpler if they're
Yeah, exactly. Right. It's simpler. Don't try and make a problem more complex than need be. If you're trying to measure a distance or a size of something that's very easy to do, then you probably just want to use normal machine vision. Don't need to get into deep learning for simple stuff. So if you've got something complicated that conventionally people thought humans had to do, that machines couldn't do, you might have to get into deep learning. So keep it as simple as possible. And people overlook traditional machine vision techniques quite a lot nowadays. There's worry about deep learning straight away. So I want to get into that. I want you guys to get into that so you know what basically machine vision is all about, the basics of it. And the LabVIEW is very good for that. It comes with so many functions for that. I was talking about that. Oh yeah, so this, right, Alcock and Thomas, this book's got a lot of traditional machine vision techniques in it, which I talk about in the course quite a bit. Yeah, okay. Oh, this is the book that Mel wrote. Okay, he's the lead director of the lab, the machine vision lab in the BRL, and you guys can come around if you want to see what we're doing sometime. He wrote this book on photometric stereo, really based on his PhD, and the reason why I recommend this one is that he goes into a lot about how photometric stereo works. And I don't know if you remember that I talked about it last week, but it's a little bit complicated. Well, it's not the most well-known technique, but it's pretty useful. We've used it for 20 years. So it's worth going have a look at that to get some perspectives, because it isn't covered in that many books, because it's only recently there's been a resurgence in interest in it, really. So it's not covered in Alcock's book, for example. Does anybody remember what photometric stereo is good for?
Distance.
Faces.
Distance? No, it isn't good for that. Faces, does someone say? Yeah, that's true. That's true. But I mean, could you be a bit more specific?
As in identifying. Was it identifying the pigs, whether they're stressed or not?
Not really, right? Because the pigs, so the work we've done on the pigs was using normal webcams, where you take an image of the pig having a drink or getting stressed, as you said, and then you use deep learning. Okay? So deep learning, photometric stereo doesn't have to involve deep learning. Photometric stereo, there's two different. Photometric stereo is a machine vision technique involving cameras and lights, whereas deep learning is a modelling technique or pattern recognition technique, like CNNs. So what does it give you? What can you get with photometric stereo? Yeah.
Like texture?
Yeah, exactly. But the important thing again, right? In machine vision, when people say texture, researchers, they mean patterns, right? I mean, if I took a picture of this floor, the machine vision experts start talking about texture in the image. But what you're talking about is 3D texture, right? Like most people, when they talk about texture, are on about a 3D texture, right?
Not the same.
Well,
How's it different?
well, the difference is that a webcam or something will just give you a 2D texture, right? Or what I call a pattern to avoid confusion, actually. A pattern. But this, you're right. Photonic stereo will give you the actual texture in 3D. You know, so it gives you this thing. Remember I talked about the bump map, the dense array of surface normals. And each point where you normally have an image, you've got a vector, which is the normal to the surface at that point. And this is dense, so you've got a dense array of surface normals, and that is a 3D texture. So that's it, yes, right. So it's very good for separating 2D and 3D data. The reason I label these stuff, which is the kind of thing I ask in the exam all the time, sort of stuff. So we might well label it. But, all right, then, well, we'll go over that again. We'll go over photonic stereo again. So we're starting from the basics. Okay, how do we recognise simple objects? Well, in this case, it's a bunch of fruits. Talking of which, we had a project working for a big lettuce harvester in Lincolnshire, and we used machine vision. I think we used deep learning, actually, having said all that, to identify where to cut that lettuce. Where to cut that lettuce, right? Because if you're automating it, you don't want mechanically a lot of people having to keep adjusting things all the time. So that worked pretty well. That worked pretty well. Why? What do you think? Well, that's not a fair question, is it? It worked well. It would have worked better if the leaves, it sounds obvious, right? If the leaves of the lettuce hadn't fallen in the way and obscured the actual stem of the lettuce. And they were getting on to us about that. But, you know, we can do a lot with machine vision. We can't really see through things, you know what I mean? Another one they wanted us to do, the company, was making salads. They got a load of salads growing in the field. They got stuff going on below the salad level. They wanted us to start looking at that. And can we start measuring things under the salads, right? So I thought, well, we might be able to do something with some radar or something, you know. But so a lot of people ask you a lot of difficult stuff. This here is a nice project we had with the National Composites Centre, looking for defects, and this was with Airbus, defects in composites for wings, which has just been completed, and there's a presentation going to happen on the 13th for that. Very successful project with the National Composites Centre, which is at the Technology Park. We run projects with them. What was there anything on the last bit? So we had input, seen image, output is the out. So we put an image in, we get out some useful information, right? Basically, that's it. That is machine vision in a nutshell. It's automatic. Autonomous systems, we've got to understand the environment. Okay, we're looking to do that a little bit at the physics of information and advanced AI techniques. Right? So, yeah, but most powerful sense. What's the second? If you're looking at robotics, vision, I would argue, probably is the most powerful sense. What do you think the second most powerful sense is in robotics?
Touch.
Yeah, tactile sensing. Yeah. Because if you put a nut in, if you're putting something in, you know, doing something that humans find simple, like putting a nut on the end of a bolt, that is difficult for a robot. You need tactile force feedback to get that to actually work. But anyway, vision is the most important, I would say. So here we got a typical image, unfortunately it's of the Bayou Tapestry, I don't know why. No, I should have put something else in there, shouldn't I? I put Trafalgar or something. But anyway, sorry about that. The thing is, so normally, suppose you had 100 by 100 pixels, right? You got 10,000 bytes of data, right? Now, if you had a colour image, like a typical old-fashioned TV 625, actually, how many bits of data, how many bytes of data would you have? 625 times 625, what's that equal? Eh? What's that? Well, it doesn't equal 300,000 or something, is it? No, more than that. 400,000. It doesn't equal 1.17 million, does it? What, eh?
I don't know, I think it's like 5 to the power 6, which is a big number.
Have you got a calculator, anybody? Everybody's carrying a calculator with them. Why does it not equal 1.17 megabytes? Have we got an answer yet on 625 squared?
90,600.
Right, thank you. Because everybody's carrying with mobile phones. 390,000, why does it not equal 390,000? Equals 1.17 megabytes. You haven't got an answer?
Is it like compression or something?
No, it's just simpler than you think. It's simpler than you think.
Because it contains
Yeah.
1 byte is 8 bit.
What?
1 byte is 8-bit.
No. I wasn't trying to capture it as something clever or anything like that. It's just a very straightforward answer to this, actually.
Is it because it contains colours?
Correct, colours, yeah. So we've got colour information here. What are the primary colours of light?
RGB.
What?
Red, green, blue.
Yeah, red, green and blue. I thought someone was going to say yellow, cyan or something like that. Red, green and blue. So we have red, green and blue image to make the colour image. We combine them to make the colour image. Okay, then the lens, right? We've got the lens. This is also, I mean, pretty standard stuff. What we're trying to do in machine vision is to do a crude simulation of all this, I guess. If you look at the human eye, by the way, and I won't read it. I'm not going to stand here reading out what it says on the slides, right? I'm just going to, because you can read that. But if you've got the human eye, when you're trying to read something, right, you're looking at a newspaper or a book or something, you're looking at a couple of letters and a word. How many of these letters can you focus on in the word? That's that? One, which is pretty bloody small, isn't it? One. So that's after, I don't know how many million years of evolution of a big brain, we can only handle a high resolution of one in a field of view, which is pretty big, 130 degrees or whatever. So you can see there why, even with humans, the ability to deal with high resolution is very intensively prior requirements in machine vision. So, you know, even the human evolution has not given us a wide. It'd be difficult to interpret the data, actually, if you had high resolution on a very big area. So this is an important point when it comes to machine vision, because you don't necessarily want to go crazy on the cameras, on the resolution of the cameras, actually. Most of the vision applications that we do, we probably wouldn't go above 5 megapixels. Yep.
Can I just ask about, so you can focus on one letter at a time. So if it's a word you've never seen before, you do it one at a time. But like the word human, I've seen that for however many years. I don't feel like I read it, go H-U-M-A-N, and go, oh, that spells human.
Well, this is vision process, isn't it? I think what I think
It's pattern recognition.
Do I not just see it as a shape and go?
My feeling is that you look at that middle letter, right, and you can see that in high resolution, and then the resolution of the image decreases the further you get away from the retina focus point, right? What do they call it? Yeah. The retina is where the high resolution is, in the back of the eye, and then on the rest of the eye, there's less of these cones and rods, and so the resolution decreases steadily until it gets quite low resolution at the side. The eye and the brain can see, I think, the central letter, and then it can see these other letters in low resolution, and it can work out what they are. Or it can work out the word. It's sort of doing a pattern recognition on it somehow, I think.
Right.
I don't know. That's I'm not an expert on human vision, I can't tell you, but I'm more into machine vision. I think that's what's going on there. Yeah. You buying that, right?
Sorry?
Is that convincing for you? Does that answer your question?
Well, I suppose in some ways, if you see it as if you see things as a pattern, it becomes quicker.
Yeah.
So
I think that's what's going on. It's
if
a
you
pattern.
learn patterns rather
Yeah.
than as humans, you learn patterns.
You're learning patterns. You're not looking at each individual letter and you're just looking at the pattern. I think. I mean, we can work out what those letters are, even though they're low resolution than the centre one, I think.
Yeah.
So I think that's what's going on there. Yeah.
Okay.
Yeah. So what we're trying to do, in our case, we've got light, okay. There's nothing too complicated here. What's that?
They're just going to my vision.
All right. So brilliant.
Sorry, Justin.
Can we make it brilliant? Can we just in your eyes?
What are we talking about? I want to stop at, this is what the analogy is for humans and computers, right? So I won't necessarily spend a lot of time on this. What we've got here is a 2D representation of a 3D world. We have a 3D world projected onto a plane, which is the sensor in the camera, okay? Then we build up the image. Now, for some reason, I think it's historical reason, right? It's probably because you read this way, but you start at the top corner, you might expect to start at the bottom, you usually start at the top there. And each number, of course, is the value of the brightness. And how many numbers are we going to have?
Brightness.
Yeah. If you've got, there's different types of images, right? There's different types of images. We'll start thinking about, we don't use colour much in machine vision, like we use in black and white most of the time. Now, if I've got a grayscale image, each pixel, all I need to know is the brightness. And normally, you might have a 8-bit image. So each pixel can be graded in brightness using 8 bits in a computer. Right? Now, how many individual grade levels are there if I'm talking about 8 bits?
256.
Right. Section written in front of me, is it? Oh, Jesus.
From 0 to 255.
Exactly.
Including 0.
Yeah. Computer will count from
No,
zeros.
it's 256 without. It's 256 different ones, but it starts from 0. And the
Yeah,
last
0 is
number-
black.
The largest number is 255.
Yeah, 0 is black and white's 255. You can get more grey levels if you want. A lot of the time that'll be enough. We don't necessarily need a huge number of grey levels. And the brightness is related. So you get a binary image. What do you reckon the binary image has got in it?
Yes or no?
So what is that?
Black or white?
So
Black or white?
what are the pixels and the values?
Oh, 1 bit, 0, 1.
Right. 0 and, did you say 1?
1, yeah.
No. Well, yeah, you're right actually. Sorry, you were right. Yeah. But the reason why I sort of labour this point, right, is that everybody, I mean, you're right. It's a binary which got 0 and 1.
No, a bit is binary.
Yeah.
A byte is 2 to the 8, so
Yeah.
256.
So the binary has got 0 to 255. Now, whereas a bit is 0 and 1.
Well done.
This guy's the expert on bits and bytes, by the way. But the thing is, why I stress this point and labour this point, as I'm trying to save you guys some grief, right? Because when everybody's starting to lab you, at least me and just everybody else I've spoken to, when they start displaying images, you've got to tell the thing what kind of image you're going to display. Okay? You have a function called display, or whatever it's called, in LabVIEW, and it gets a WinDraw is what draws the image. Now, if you then put a palette into this thing, WinDraw, to get it to draw a certain type of image. Now, you know, I think it defaults to grayscale. So what happens if I put a binary image into this thing that thinks it's going to display a grayscale image? Now you know this because you're the expert in this.
Could you ask the question again?
Yeah, the thing will default most likely to, it thinks it's going to display a grayscale image.
Yeah.
But I've got myself a binary image.
Yeah.
I'm trying to display it. What do you think will look like on the screen when I do that?
It's going to be a shadow with a bit of white somewhere.
No,
Is it
it's
not
going to be
binary?
entirely black, you're right. And this is something that screwed a lot of people up because, yeah, where's this black screen going from and so on. So, because 0 and 1 are going to look black to you if you're displaying and thinking it's a binary image. So, yeah, so binary images. What, does anybody happen to know what the process is called that takes you from a grayscale image to a binary image in machine vision or computer vision?
Binarisation.
Yeah, right, brilliant. Yeah, but there's a particular function, if you know what I mean. It is binarisation. There's a particular function which is often used in machine vision. I mean, there's a name for it. You know.
Like polarising or something.
No, polarising's got to, ask Harry about polarising, he's just PhD in it. Polarising is to do with the nature of the light. Yeah, but it's just thresholding, right? Thresholding is when you turn a grayscale image into a binary one, and the level of the threshold, and this is what you'll play around with the vision system, will really, really determine what it looks like after you've done your binary on it. So, there we go. And that's what they're talking about here, isn't it? Examine all grey level to binary image I was talking about. You see what all this slide is, can't you? Look at it, a 3.5-inch IBM disk drive here. So we get the image on the left there, we're doing our threshold, and then we're doing the edge detection. Does anybody know anything about edge detection at all? What do you know about it?
Detects like the difference between one car and another, doesn't it?
You can detect like a line of pixels,
A line,
essentially.
yeah.
Yeah, it creates a line where there's a where there's a difference, doesn't it? An edge. Do you happen to know how it works at all, you guys?
I think it just looks for like, you set a threshold of say, there's an edge when there's this difference in colour. It'll scan along, and the first instance it comes along, it'll stop there and say that's the edge.
Yeah, I mean, really, it's edge detection uses a type of filtering. You know, I talked last week about filtering a bit.
Yeah.
I'll go through this later in more detail, but it uses a kind of filtering where you put a little kernel over it, and then you multiply the pixel value by the kernel, you add it all together, and then it gives you, depending on what the values are in the kernel, it gives you an edge. There are different types of edge detector, but that's basically how it works. So image processing generally works like that. It works like what you might call filtering, or it's also called convolution. Okay, convolution. And that's where the convolutional neural network comes in, because the convolutional neural network is using that to actually identify features in the image. Anyway, I'll go into all that later. But this is an example of keeping it simple, isn't it, really? You've got all this complexity, look. You're simplifying it, reducing the data to just black and white, and then you're finding the edges, so you're reducing the amount of data you're looking at, and then you're just measuring a distance. This is what I was talking about, keeping it simple with machine vision, traditional computer vision. Now, in the session this afternoon, as I say, you guys have all the excitement of getting into Vision Assistant with Colette. And when you start it up, you'll get this kind of screen. So you want to, this is pretty self-explanatory, I think. You can grab images with it in snap, grab, and sequence. There are different ways. Snap is the simplest. Grab is if you want a precise image capture at a certain time. And sequence if you want a load of images sequenced. What you'll do actually in this module is you'll go downstairs into the digital gallery and you'll use some software that Scorpion gave us from a company called Hikvision. So actually it doesn't use those. You'll use those in the tutorial for learning about LabVIEW, but when you come to actually grab your image, it's very easy to use software that they gave us for doing that. So, Andy will show you how to do it, no doubt, if you just go in there. Send him an email if you want to go down there, by the way, because he operates in that way. He sort of has it at certain times. Yeah, so when you run Vision Assistant, it looks like this. So you get your image up here, and then you start applying different functions to it. I think what's clever about it is that it starts generating LabVIEW code at the bottom of the screen automatically. When I started learning this, nobody knew anything about it, of course. I was just by myself, as you can imagine, in the year 2000 or whatever. And it didn't do that. It just wasn't capable of doing it. So I had to sort of look at the scripts it generated and try to work out. LabVIEW is a type of programming language. Does anybody know anything about it, or has used it?
Just like a small bit with Gary last term.
Did you?
Yeah.
What do you know about it?
It's not much, but we had like little black plastic plates. We found where the edges were, found where the holes were, relative to like a datum point.
Really?
And we measured the length and width.
Yeah, similar to what you're doing this assignment. I mean, basically, do you remember anything about the language itself?
No, it depends on how you're asking.
It is, okay, what I was trying to get to is it's a graphics language, a G language. No, normally, right, and this does a lot of people's heads in, who are into programming, but normally you have a sequence of a sequential language, don't you, in BASIC or C. You write a line of code, line 10, you write another line of code, line 20, and it operates sequentially. This doesn't work like that. It works by means of data travelling along wires, okay? And these icons are connected together by wires. And what it does is it controls the procedure by how the data flows along a wire. And I'll go through this in more detail later on. But actually it's easy to use. It's nice to get into. I quite enjoy messing around with it. But a lot of people are so dyed-in-the-wool computing hacks that they can't get it. They don't want to do that. So they developed something else called Lab Windows CVI, which is a version of C, which has all the iMac Vision LabVIEW functionality for image processing. But you don't need to worry about that, because you'll be using, for this assignment, Vision Assistant to get into it, and then LabVIEW, most likely, to the actual program, okay? Which I think you'll quite enjoy using, actually. It's quite a nice thing to get into. They spend billions of dollars on it, so it's quite well developed.
Is that like Vision Builder? Is it the same?
Vision Builder, right, is very similar to Vision Assistant.
Right.
So if you know about Vision Builder, you won't have any problems with Vision Assistant. It's a little bit simpler than Vision Builder. And they're all similar in that they basically are high-level shells that use LabVIEW for image processing. That's what they are. So if you did a bit of Vision Builder, did you?
Yeah, that's what we did with those little rectangles from Gary.
Oh, yeah, he's into Vision Builder. But this is Vision Assistant, it's a very similar thing. Yeah. Basically. But it's a nice introduction, I think, to machine vision, because you can see all this capability of image processing, and you can see this automatic generation of code. The thing is about the automatic code generation is that it works nicely, but if you want to use something a little bit complicated, with maybe questions and, is it so-and-so, you want to have a bit of programming control, then you can't do it like that. You have to start programming yourself, if you want to start making decisions in the code and such, depending on the outputs of the image processing. This will all be, so it makes sense when you get in and start playing around with it. So this is just a little bit of a Vision Assistant tip in relation to what, you know, getting into it a little bit, preview window, and this is all explained in the tutorial as far as I remember. Yeah, scripting feature. Yeah, so you run scripts on single images. So what this thing does, right, is it generates a script, Vision Assistant typically. But it also, but the script is just a list of functions, image processing functions that you're going to use on an image, and the parameters associated with what level you're going to use them at. You might use a threshold and level 100 or whatever. You know. And then you can do a bit of processing to turn that into a lab. The system will turn it automatically into a LabVIEW program for you. And it will even turn it into a C program, actually. It's got a lot of capability in post-processing. So, you know, when it comes to the assignment, you could start, I mean, in subroutines, if you're into this programming at all, are normally for doing little tasks. And so you generate subroutines to do a specific programming task, right? In LabVIEW, these things are called VIs, virtual instruments. They're little, like subroutines. You can either generate them directly by doing a bit of LabVIEW programming, or you could do a little bit of Vision Assistant work and have them generated for you, for instance, and then combine them to do the assignment. So I'm not saying you have to do the assignment in any particular way, as long as you get it working and using LabVIEW. You know, as long as you do what's asked for, that's fine. Exactly how you do it is up to you. Any questions about that so far? G-code is what they call it. It looks a bit like a circuit diagram, but it's not. It's a bit of G-code. It was developed in California, I think, for data logging. It's used a lot in data logging, you know, measuring heights of water and out in the field, isn't it? Oh, there we go. Well, I'd normally put this at the end of the lecture, right, somewhere near the end, to show you what you can do. Human vision, we talked about earlier, is brilliant, isn't it? But it can be fooled. But with a computer, with computer vision and machine vision, what you see is what you get. I think that's a type of deep learning, actually. No, that's you already looked once, sorry. But what I'm saying is it tells you about where it actually got there. In this optical illusion, the brightness of square A is the same as the brightness of square B. Now, I showed this to some students a couple of years ago, and they said, no, it's not. And I said, bloody is, you know. And what you can do is, if you don't believe me, I suppose, is save it as an image, and then start getting Vision Assistant going, and start measuring the brightness in those two areas. That goes to show how powerful, I mean, I don't know about you, but I think that's pretty effective, the optical illusion. So. But here we go.
So you saying that the system will show the same brightness on A and B?
Yeah.
Okay.
I know that does your head, but
yes.
It's like it.
Yeah.
I mean, even if I get the picture, right, and I cut a couple of holes in some paper and put that over it, it'll look the same. But when you look at all that stuff, it looks wildly different. They didn't believe me. They didn't believe me 2 years ago, I'll tell you. But, so that's it. Oh, here we go. What I've got here, I don't know how much do you want me to go through, because I've got quite a lot of this stuff, and I can go through it anytime I like. But I thought I'd just do a little bit of background. We did this project, and Gary did this actually again. He rigged this thing up, right? If you come into the machine vision lab, you can see it. It's called the photo face rig. We still got it. He rigged it up when he first joined this place years ago. And he told me, we took it to South Wales. The idea here is that you're going to get the next generation of face recognition system for airports. You get much, much better reliability in airports. None of this, you know, fooling it by spoofing it stuff. You're going to measure the face in 3D. So we got this grant, I think it was £1 million, from the EPSRC for developing the system, 3D face recognition. This is some bloke who was involved in. This is actually using photometric stereo. This is using the technique I was talking about earlier. And you can see that this, right, is most likely a rendering of the bump map. It could be. If you have a bump map, how in the hell do you visualize that? It's just a load of vectors, isn't it? How in the hell are you going to visualize that? But you can visualize it and make it look like a surface there. And the way to do it, right, is to rig up in the computer a virtual light source. Right? You can put the light source wherever you want, but you know where it is. And you've got the lighting model. This is maybe not totally clear because I haven't gone into photometric stereo yet, but basically you've got a lighting model that tells you how bright you expect it to be if you've got a light in a certain position. So you apply that to the bump map and you end up with that. So it's quite easy to get a visualization of the 3D data just doing that. And you can see what it does is it effectively removes the pigment. All you've got is this 3D data. So one thing you can do with it, what's quite useful, if people want to fool people a little bit by means of making their face look different, they can apply makeup to make their face look thinner. And that is quite fooling a lot of people, but with this system it would see through that because it would remove that makeup and then you just have the shape of the face. Which you can't change, can you really? And you can't really change the shape of your forehead or your nose. Or if you're mad enough to have plastic surgery, I suppose you could. But, yeah. I don't know. So that's it. That worked quite nicely. Oh, and that's Gary there going into the machine. This thing started off with, I won't go to everything here, I'll just talk a little bit about this, but this thing started off with visible lights. We used some photo flashes from a photography place, and the trouble is we took it to General Dynamics, who were collaborating, and we had this thing flashing away, and they said, bloody hell, it's no good. So then we replaced them with near-infrared lights. What is a near-infrared light?
It's on the spectrum, but it's not red, it's nearly red.
Right, exactly.
Just
so,
enough that you can see it.
No, so you can't see it.
Oh, okay.
Yeah, because if you've got the electromagnetic spectrum, right, you've got all these colours, right, you go in, invisible light, 500 nanometers, you're going into 600 nanometers. What sort of colour have you got when you go into 650, say? Sorry?
Black.
No. Black? Did someone say black?
Yeah.
You trying to take the mickey? Oh, I could use another word, I suppose. It's trying to take the piss or something. No, black.
Isn't it purple, I think?
No, you guys are getting it wrong, right? Because when you go into, when the wavelength gets longer, right, the light goes towards red. Purples and blues are at the other end, on the short wavelength. So the wavelength gets longer, you go into the red. And then, at 700 nanometers, you suddenly can't see it. Right? And then anything longer wavelength is invisible. And that stuff, 700 onwards sort of thing, is in near infrared. And that's why I say be careful, be very careful with this LED, because it's up in the visible range. So that's that, yeah, so then it worked better. It worked better in near infrared than in invisible light. And of course it didn't disturb the people at General Dynamics because nobody knew it was operating. I rigged up downstairs here and we got 1,000 people go through it or something. And we generated the first 3D database on the internet of faces that wasn't involving actors. It was involving real people just walking through it, which I thought was a little claim to fame. To be honest with you, that was probably the most useful thing that came out of that project because the company didn't necessarily want to take it forward, but you do get some good papers out of it and such. Now, I can't go on anymore. How long is this meant to be? Until 20 past. I could go on if you like, but there's a lot of stuff here, and you have a look yourself, okay, at what I put on here. And if you want me to go into more detail in a particular area, I can certainly do so. I will do so in a future lecture. But we've done loads of work in all sorts of sectors. A lot of it on quite recently, it's been agri-tech and plant related. We did a project with Edinburgh University. Look, I'll just say this one thing, right? We're recovering, this is a type of plant that they grow when they're looking at plants, right? They're trying to find out what conditions are good, put it in a growing machine, put the light on, put the temp. Then we put the 3D from next to it, we get the shape. What advantage might this offer over just capturing a normal image? I'm trying to work out how fast this plant is growing, how big it's got after a week or something. I wonder how big the leaves are. What am I getting with the 3D data? Eh? Yeah, but what's useful information am I getting about the growth of the plant? You see, these leaves, they move all over the place all the time, actually. That's one pain in the ass, trying to measure it when it's moving all over the place for some reason.
Can you get like volume?
Well, it's kind of related to volume.
An estimation of the volume of the plant?
Well, I was thinking of area. Because that leaf, the area of the leaf is how much it's grown, isn't it? But if the leaf has got an angle, then you're getting the parallax effect, and you're not getting an accurate measure of the actual size of the leaf, the actual area of the leaf. So we can correct that, we can measure that angle, and we can correct and work out more accurately exactly how much it's grown, what the parameters were, and so on and so forth. Yeah, so, and there was a lot of work done on this. We had some, a PhD was very good on this, and a lot of good papers came out. We're still working on it now, actually. But there's other stuff here, but I don't think we've got time to go through it. Oh, there's a How's My Cow. Do you want me to say something about How's My Cow? This is my favourite project, actually. I live in Somerset, and I finally got a project with something going on nearby, rather than Scotland or something. and there's a farmer down there who's got this thing, we developed with them, and you're measuring the cow, right? And you want to know the condition of the cow, because you want to know, is that cow got the right amount of fat on it? Has it got the right amount of fat on it? And we use a 3D technique straight away. This is the Connect I was talking about, the sort of Mark II Connect. We've got a Mark III Azure Connect downstairs in the digital lab you can get out and play with. But this is the Mark II, so we're covering, you can see the brightness is to do with the height, the distance, the range from the animal. So we're getting all this 3D data, like, we're getting all these data points. And we had a special technique that we developed some years ago called the rolling ball algorithm, right? Which I thought was really bloody great. Right? So what you do with the rolling ball algorithm, right? You get a ball, this is all done virtually, you got the inside of the animal, right? You have the ball of a certain size, you roll the ball around inside the animal. There's only certain parts of the animal that the ball can't reach. Do you understand what I'm talking about? And the more skinny the animal is, or the angular it is, the more of the surface of the animal isn't going to be able to reach with a rolling ball. So this gives you a measure of the condition of the animal, which I think was pretty new. I don't think anybody else did that. And
Wait, I don't understand.
well, when this thing's measuring range data. Right? So it's giving you the position of the skin of the animal in 3D. So that's a 3D surface, a complicated one. You've got to analyse it somehow to work out how skinny the animal is, how angular it is. Right? So the technique was to take virtually, to get that surface, and take this virtual ball and roll it around inside, and see how much of that surface that ball can touch. If it's a very angular bit on the hip, it ain't going to be able to get up in there because the ball's going to stop it. Do you know what I mean? So you get a measure of the angularity that can tell you objectively what the condition of the animal is.
So if it's bony, you can tell because the ball can't reach the inside of all the corners.
Exactly. Yeah. So that's brilliant. Suppose we get it all working. What's the problem with trying to actually determine how well it's working? What's the problem with?
Yeah, how do you validate that?
Yeah, how the hell do you validate that? You've got a load of herdsmen who are all saying something different, they're probably having a kind of what the feeling like on the day. And it's difficult. That's sometimes a problem. You get some good data, but to get in the ground truth is a little bit tricky sometimes because I think this could be very useful on robotic, robotic, you can buy these robotic milking things. They cost so many £1 million. You send one animal through at a time. Well, you have this just before you send it through, and it tells you the condition of the animal. So you work out what the feed's like, what you ought to do with the animal. Anyway, I could stand here all day, but I won't carry on anymore, right? Is there anything else I should have told you? You've got on your timetable, you've got this. Make sure you go to the tutorial this afternoon. Colette will help you a lot. If you get any serious issues, drop me an email. Otherwise, I'll see you guys next week.
Is this on Blackboard?
Yeah, I put it on yesterday. There's a lot more stuff about what we've done, but I don't have time to talk about it.
If you want to connect,
I don't know.
Did you genuinely think there was black lights? Or was that just the spur of the moment?
Well, to be honest with you, a lot of these things are designed there. So they will just have a USB connection. I don't know about this. The thing is, there's a lot of ones as well. If you want to do a project of this, you might be able to find it.
Do you want to come sit with me and Atkins and research?
No, I need to see that.
For the tutorials, you go T134. Where is
It's BRL.
Right.
Yeah. If you go into the doors, immediately on the left, there's corridors.
Okay.
Yeah, Gordon will show you as well.
Cheers.
Cheers.
Sorry, one more question. Say we tell us in the tutorial. The software, the LabVIEW and all that, can we use that at home? Are we going to be able to get it on our laptops? Or?
Yeah, I mean, the thing is, right, it's got apps anyway, right? Apps anyway, we're able to install. And IT Online, the experts, and they tell me not to get involved. If you're having any trouble, you drop them an email, they'll probably help you.
Okay.
But I know apps anywhere, I don't know if you use apps anywhere.
I have used it in the past.
It's pretty brilliant, actually.
Yeah.
The only thing you do need to make sure you get a connection to the to the network.
Yeah.
It keeps checking for validation.
Okay.
But other than that, it's bloody great because you don't have to mess around loading it all and getting it all.
mill it out.
I mean, LabVIEW, there's so much to it.
And then machine vision that.
I think in the case of LabVIEW, it even comes with some software designed for installation.
So each
You've got to install the installation software, I think.
I'll go to the tutorial first because Colette might let us know. She might tell us what we need.
Well, she might be doing it herself.
Yeah.
I haven't actually. I'm running a lot of stuff from home. I'm not running LabVIEW from home. I don't know if she is or not, but she.
Yeah. All right, I'll ask her.
Yeah, rather than do like that, they do it like in steps, and then what they do is then when they would say it was